In this video, I'll tell you about a basic result from mathematics called Markov's theorem. And along the way, I'll introduce and use Chebyshev polynomials, which are a very important family of polynomials with some very nice properties. So here's an example of a polynomial. Okay. This is a polynomial of degree 3. Here's its formula, and this is its graph. Here's another example of a degree 3 polynomial. Now, polynomials are an extremely important kind of object. Throughout early mathematics, we learn a lot about polynomials because they're very powerful and very versatile. One of the key messages that we learn about polynomials is that polynomials can be used to approximate arbitrary nice functions. Okay, this is why they are so ubiquitous and so powerful. But polynomials do have their limitations. For example, one important limitation is that a polynomial of degree n can have at most n roots. So, for example, this is a polynomial of degree 3, and it can have at most 3 roots. It can vanish at most 3 inputs. So in this picture, we see that this polynomial does have 3 roots. Okay, and there cannot be a 4th root. So that's one limitation of polynomials. And Markov's theorem identifies another really fundamental limitation of polynomials. To explain the limitation, let me first start by defining what I mean by a bounded polynomial. I'll say that a function is bounded if the value that it takes on some fixed interval is bounded in magnitude. So for example, let's just consider the input coming from the interval -1 to 1. And I'll say that the polynomial is bounded if its magnitude on that interval is at most 1. In other words, a bounded polynomial is one whose graph passes in between these two rails here. Okay, that's a bounded polynomial. So this polynomial, this degree 3 polynomial, is not bounded. However, this one is bounded. This polynomial is bounded. And what Markov was interested in exploring is he was interested in asking this question: what are the features of bounded polynomials? Okay, so if you know that a polynomial is bounded, what else can you infer about it? Okay, what are the consequences of a polynomial being bounded? And this is a really interesting kind of question. It's very interesting to me as a theoretical computer scientist because often what I study are functions that are bounded. Okay. Things that we'd like to compute are usually bounded. And so understanding the space of bounded functions in general, that's a very interesting question. Okay, and often things that are efficiently computable are also can often be approximated by low-degree polynomials. So understanding bounded polynomials is relevant to understanding to many questions in theoretical computer science. Okay, and Markov proved a very nice property of bounded polynomials. He showed that if you have a polynomial that's bounded, then its derivative can have magnitude at most the square of its degree. Okay, so here's actually one way to state his theorem. It says that the maximum value of the derivative on the interval between -1 and 1 is bounded by the square of the degree of the polynomial times the maximum value of the magnitude of the polynomial on the same interval. Okay, so for example, this polynomial here, it's bounded and its degree is 3, and so Markov's theorem asserts that the slope of the graph here in this region can never exceed 9, which is the square of 3. Okay. Now, if this is the first time that you're hearing Markov's theorem, then I suggest you do what I always do. The first time I hear a very natural and basic result, which is that pause the video, stop listening, and think about how you would reason about this yourself. How would you go about proving Markov's theorem, or even a weaker result along the same lines? Now, the reason Markov's theorem is so interesting to me is, first, it's a very basic result, but secondly, the proof of Markov's theorem is very clever and very interesting and full of ideas. In fact, once you see the proof, you'll see that we can not just prove this result about bounded polynomials, but we understand a whole lot about the structure of bounded polynomials. All right, and the proof of Markov's theorem also has a high-level structure that I really like. It's a structure that's often used in mathematics. And the structure looks like this. We'll first find the extremal objects for Markov's theorem. Namely, we'll find the objects, the bounded polynomials that attain the most extreme behavior among all bounded polynomials, the ones with the largest magnitude of derivative. And these will be the Chebyshev polynomials. Okay. And once we've found these objects, we'll consider their properties. We'll study their properties, and studying their properties will reveal the limitations of all other objects in the class that we're interested in. In this case, understanding Chebyshev polynomials will allow us to understand all other bounded polynomials. Okay. So let me show you some examples of Chebyshev polynomials. So here's the Chebyshev polynomial of degree 1. It's just a polynomial x. And from this picture, it should be clear that, this is the bounded polynomial of degree 1 of maximum derivative. Okay, there cannot be a steeper line that's bounded. Here's the Chebyshev polynomial of degree 2. And maybe this is the quadratic that you would have guessed to be the one that has the largest derivative. Here's the Chebyshev polynomial of degree 3. Okay, and there's for every n, there's a Chebyshev polynomial of degree n. So looking at these pictures, you might start to detect a pattern, which is that the Chebyshev polynomials tend to have a lot of wiggles. They go up and down a lot, right? And if you have a degree 8 polynomial like this one, then we know that this polynomial, any degree 8 polynomial, can have at most 8 roots. Okay, and that limits the number of times the polynomial can go up and down across the x-axis. And if you look at this picture, you see that this polynomial crosses the x-axis at exactly 8 times. Okay, so this polynomial has exactly 8 roots. And intuitively, it makes sense that the polynomials that have the largest derivative will go back and forth a lot. Because, if the polynomial has a very large slope, then it will have to turn around quickly in order to avoid going past this boundary. Okay, and so that should create a lot of wiggles. Okay. All right, so in a few minutes, I'll explain where these Chebyshev polynomials come from, and I'll explain how you can compute the formula for the Chebyshev polynomials. But before we do that, let's use the structure of Chebyshev polynomials already to prove something about all bounded polynomials. Okay, so I'm not quite going to prove Markov's theorem yet, but I want to prove something else that holds true for all bounded polynomials. So here's a Chebyshev polynomial of degree 3. This is what it looks like. And now I want to use just this picture, the structure of this polynomial, to prove a general fact about all degree 3 bounded polynomials. So here's the fact that I want to prove. I'm going to claim that there cannot be a bounded polynomial of degree 3 whose leading coefficient is 5. Okay, namely the coefficient of x cubed cannot be 5 if the polynomial is to remain bounded. And actually, more generally, what the proof will show is that for any n, there's no bounded polynomial of degree n whose leading coefficient is larger than the leading coefficient of the nth Chebyshev polynomial. So here, the leading coefficient of the third Chebyshev polynomial is 4, and that's why there cannot be a bounded polynomial of degree 3 with leading coefficient 5. Okay, so let's prove it. In order to prove it, I'm going to appeal to a fact that I've alluded to a few times already, that any non-zero polynomial of degree n can have at most n roots. If p of x is non-zero and has degree n, then p of x can have at most n roots. Okay. And how can I use this fact? Well, again, I'll suggest that it's a good time for you to pause this video and try to think about how you would use this fact to prove the claim yourself. Okay, to prove the claim, I'm going to construct a polynomial of degree 3 that will have many roots. Okay, using a purported polynomial p of x of this form. Now, how will I do that? Well, consider the polynomial t3 of x minus p of x. Okay. Well, let's draw the curve for p of x. So imagine that you have p of x here, goes through. P of x is bounded. And now you see, every time the graph for p of x crosses the graph for t3 of x, that generates a root for this polynomial. So from this picture, you see already that this degree 3 polynomial must have 3 roots, at least 3 roots. Well, actually, the picture is a little bit misleading, because it could be the case that the curve for p of x does something like this, and this might generate only 2 roots for t3 of x minus p of x. But there's a way to fix that. Okay, there's a way to fix that. Just pick a parameter lambda that's very close to 1, but less than 1, so that 5 times lambda is still larger than 4. Okay. Pick such a lambda. And now let's look at t3 of x minus lambda times p of x. So we'll scale p of x by a number that's slightly less than 1. And now, since lambda times p of x does not touch the boundary here, because p of x is bounded, it must really be the case that lambda times p of x intersects t3 in 3 places. So this generates 3 roots for t3 of x minus lambda times p of x. Okay, so this has 3 roots. And now we'll use the fact that the leading coefficient of p is 5 to show that there actually must be a 4th root. There must be a 4th root. And to see this, we just need to step back from the picture. So let's zoom out really far away, and now let's plot lambda times p of x. Well, lambda times p of x, it has to generate 3 roots in this region, and then it comes out here, and I claim that at some point far away, lambda times p of x has to cross t3 of x again, okay, which will generate a 4th root. And this is because the leading coefficient of lambda times p of x is larger than 4. So for x that's very large, lambda times p of x has to have a value that's larger than the value of t3 of x. Okay, so lambda times p of x exited the interval here below t3 of x because t3 of x has the value 1 at this point, and lambda times p of x has a value less than 1. But eventually lambda times p of x must exceed t3 of x. So this generates a 4th root. Okay, so this shows that t3 of x minus lambda times p of x will have 4 roots if there is such a p of x. And that's not possible. Okay. So t3 of x minus lambda times p of x is a non-zero polynomial by construction, and it has degree 3. It cannot have 4 roots. So there cannot be such a polynomial p of x. Okay, so I hope you see that we used many nice properties of Chebyshev polynomials to reason actually about all polynomials that are bounded in this proof. Okay, so next let's turn to understanding where Chebyshev polynomials come from. As I suggested earlier, what we really want is a polynomial that has a lot of wiggles, that goes really back and forth and remains bounded. Now, we don't know a polynomial that does that immediately, but there is a function, there are a number of functions that we do know that have that structure. And those are the trigonometric functions. So for example, here is a plot of cosine n times theta. And this function has tons of wiggles. Okay. Now, unfortunately, this is not a polynomial. It's not a polynomial. However, you can use it to construct a polynomial, and that's exactly what the Chebyshev polynomial is. You can do that by observing that cosine n theta is a polynomial in cosine theta. It can be expressed as a polynomial in cosine theta. And that polynomial is the Chebyshev polynomial. So the Chebyshev polynomial is the polynomial t sub n that satisfies this equation. Okay, so it should not be immediately obvious that there is a polynomial t sub n that satisfies this property, but now I will explain why that's the case. Okay, so let me prove to you. So the claim I want to make is that there is a degree n polynomial t sub n satisfying that t sub n of cosine theta is equal to cosine of n times theta. So let's prove that this is true. Now, this fact follows from some pretty standard trigonometric identities. And one way to see that it's true is to use the identity e to the I theta is equal to cosine theta plus I sine theta. Okay, so this is an identity that I will not prove, but one consequence of this identity is that you can express cosine, so here's a claim that I'll make, cosine of alpha plus beta plus cosine of alpha minus beta can be written as the real part of e to the I alpha plus beta plus e to the I alpha minus beta. And I claim that that's equal to 2 times cosine alpha times cosine beta. Okay. I'm not going to prove that, but I'll leave it to you to verify that if you apply this identity once with e to the I with theta equals alpha, once with theta equals beta here, write this as the product of two such terms, and write this as the product of two such terms, and calculate what you get, you'll see that the real part of the complex number that you get is exactly this number. Okay. Now, so once you have this formula, in particular, this means that cosine of n plus 1 times theta plus cosine of n minus 1 times theta is equal to 2 cosine of n theta times cosine of theta. And now we're ready to understand the polynomial t sub n. So we'll prove that there is a polynomial t sub n of degree n by induction on n. So for the base case, let's first check what t sub 0 is. Well, cosine of 0 times theta is just 1, which is a polynomial of degrees 0 in cosine of theta. Right? It's just the polynomial whose value is 1. Cosine of 1 times theta is equal to cosine theta, which again is a polynomial in cosine theta of degree 1. Okay, so those two cases are fine. And now in general, by this identity here, we can write cosine of n plus 1 times theta is equal to 2 times cosine of n theta times cosine of theta minus cosine of n minus 1 times theta. But by induction, cosine of n theta is a degree n polynomial in cosine theta, so it's 2 times t sub n of cosine n theta, of cosine theta, times t sub 1 of cosine theta minus t sub n minus 1 of cosine theta. Okay, which is the definition of t sub n plus 1 of cosine theta. So you see, this expression here, by induction, this is a degree n polynomial in cosine theta. This is a degree 1 polynomial in cosine theta. So this is a degree n plus 1 polynomial in cosine theta. And this is a degree n minus 1 polynomial in cosine theta. So the result of this calculation is that cosine n plus 1 theta is a degree n plus 1 polynomial in cosine theta. Okay. So this tells you actually how to calculate t sub n plus 1 from t sub n and t1 and t n minus 1. Now, one nice consequence of this here is that, of this formula, is that t sub n must be bounded, right? Because when the input t sub n, input to t sub n comes, is a number x that's between minus 1 and 1, then such a number can be viewed as cosine theta for some angle theta. And since you have this equality here, the output must also be of the form cosine n theta, which means that the output of the function has magnitude at most 1. Okay, so t sub n is a bounded polynomial. Next, let's understand its derivative to see how large it can be. And to do this, because we have this nice formula, t sub n cosine theta equals cosine of n theta, we can just take the derivative of both sides, and that gives that the derivative of t sub n cosine theta times minus sine theta is equal to sine minus sine of n theta. Oh, minus n times sine n theta. Okay, I just use the chain rule to take the derivative of both sides. Okay, so rearranging, this gives us identity. As long as sine theta is not 0, I can divide by sine theta on both sides, and I get that the derivative of t sub n at cosine theta is equal to n sine n theta divided by sine theta. All right, so to understand the derivative now, all I need to do is understand this expression. And again, it's helpful to use the identity we saw before. Let me write it down here again, that e to the I theta is equal to cosine theta plus I sine theta, which is a consequence. We get that sine theta has a nice expression. Sine theta is equal to e to the I theta minus e to the minus I theta divided by 2i. And that means that we can express sine n theta divided by sine theta. Applying this formula twice, we get that it's e to the I n theta minus e to the minus I n theta divided by e to the I theta minus e to the minus I theta. And this looks like a standard formula in algebra. It looks like a to the n minus b to the n divided by a minus b. Okay, for which there's a nice expression. This is a to the n minus 1 plus a to the n minus 2 times b plus all the way up to b to the n minus 1. Okay, the way you can prove this, if you don't remember, is you can multiply this with the denominator here, and then you get a telescoping sum. All the terms cancel out except for a to the n and minus b to the n. All other terms cancel out. Okay, so this means that you can express this thing. Now if you plug back the values of a and b here, you get e to the I n minus 1 times theta plus e to the I n minus 3 times theta all the way up to e to the minus I n minus 1 times theta. That's a nice formula, and it means that there are two consequences here that are nice. The first is that sine n theta divided by sine theta, the magnitude of this number is always at most n. And that's because what we have here is the sum of n complex numbers, each one of magnitude at most 1. Each one of magnitude at most 1. Okay, so their sum will have magnitude at most n. And that already proves that the magnitude of the derivative here, this quantity, has magnitude at most n squared. So let's call this. Okay, so this means that this has magnitude at most n squared. And the second observation is that the limit theta going to 0 of sine n theta divided by sine theta is equal to n. As theta gets very close to 0, what happens to each of these numbers? Each of these numbers becomes very close to 1. Right? Because it becomes very close to e to the 0, which is just equal to 1. So the value of the derivative of Chebyshev of the Chebyshev polynomial when theta is close to 0 is equal to n squared. So the Chebyshev polynomials have the derivative that's bounded by n squared, and they achieve the value n squared when cosine theta becomes very close to 1. Okay. All right, so that sort of establishes that, assuming that Markov's theorem is true, then Chebyshev polynomials do achieve the largest possible derivative of all polynomials of degree n. Okay, but we have yet to prove that Markov's theorem is true. And next, we'll use the properties of Chebyshev polynomials and these functions cosine and theta to actually prove Markov's theorem. But actually, first we'll prove a slightly different theorem that's related, called Bernstein's theorem. Okay. And then Bernstein's theorem will be helpful eventually to prove Markov's theorem. So let me tell you about Bernstein's theorem now. Bernstein's theorem is about trigonometric polynomials. So let's say you have a function f depending on theta, which can be expressed as a polynomial in cosine theta, which is, just like a Chebyshev polynomial, right? Chebyshev polynomial is a polynomial in cosine theta, or cosine n theta is a polynomial in cosine theta. Then what Bernstein's theorem says is that the magnitude of the derivative of f can be bounded by the degree of the polynomial p times the maximum value that f takes. Okay, so if, for example, f is bounded for the values theta between minus pi and pi, then the derivative can attain the value at most the degree of p. Okay. Okay, so to prove Bernstein's theorem, we're going to apply, we're going to use, again, the extreme objects. And the extreme object here is cosine n theta. Because if f of theta is equal to cosine n theta, then the derivative of f is equal to minus n sine n theta, which certainly attains the value n when sine n theta has its maximum value of 1 or minus 1. Okay, so this polynomial cosine n theta, this trigonometric polynomial, is the extreme object for Bernstein's theorem. Now, intuitively, what I'd like to do is I'd like to take an approach similar to what we did before. I'd like to plot. Okay, so I have this extreme object cosine n theta, and here's its graph. I'd like to take some other f, okay, and argue that if this f has a very large derivative, then I'll obtain, because cosine n theta goes back and forth across this interval many times, I'll obtain too many roots for cosine n theta minus f. This is a high-level strategy that I would like to employ. But there are a few challenges in doing this. Okay. The first challenge is that f is not a polynomial. So I can't, it seems like I can't take the difference of two things that are not polynomials and use the fact that polynomials can only have a bounded number of roots. That's the first challenge. And the second challenge is that f might do something funny, like go and touch the boundary, okay, like this. But this is a challenge we've already resolved earlier, right? We can resolve this challenge by considering the curve of lambda times f, where lambda is some number very close to 1. And this will ensure that you really cross through the middle of this interval here and get a lot of roots. Okay, so these are some of the challenges. So now let me address the challenge that f is not a polynomial. Okay, so I can't talk about the roots of f or something that's the roots of cosine n theta minus f. Although f is not a polynomial, it is a polynomial in cosine n theta. So this is what we'll use. Okay. So once again, we're going to use the identity we saw before, that e to the I theta is equal to cosine theta plus I sine theta. Now, a different consequence of this is that cosine theta can be expressed as e to the I theta plus e to the minus I theta divided by 2. And therefore f, or in this case lambda times f, you can write that as lambda times p of cosine theta, which is equal, because p is a polynomial of degree n, okay, let's say the degree of p is n, it's equal to e to the minus n theta minus I n theta times lambda times v of e to the I theta, where here v is a polynomial whose degree is at most 2 times n. And that's because when you plug in for cosine theta this expression, you end up with a bunch of powers of e to the I theta, and these powers range from minus n to plus n, minus n to plus n. And if I take out a factor of e to the minus n theta from whatever I get here, I'm left with a linear combination of powers in e to the I theta that range from power 0 to power 2n. Okay, so that means I can express lambda times f times theta as e to the minus I n theta times lambda times a polynomial of degree 2n in e to the I theta. So I've now obtained really a polynomial in some complex numbers. Okay. And I can do the same thing for the Chebyshev polynomial. So similarly, the Chebyshev polynomial is equal to e to the I minus I n theta times some polynomial w in e to the I theta, where w again is a polynomial of degree at most 2n. Okay, so now I want to consider, when I look at cosine of n theta minus lambda times f of theta, this can be written as e to the minus I n theta times w of e to the I theta minus lambda times v of e to the I theta. And so every root here every point where the curve for lambda times, the graph for lambda times f theta intersects the graph for cosine n theta must contribute a root, a complex root, potentially, of the polynomial w minus lambda times v. And if you think about cosine n theta, it crosses this interval 2n times. So already the picture shows that this polynomial has at least 2n roots. 2n roots. Okay. Now the key point is that e to the minus I n theta is never 0. Okay, so every time this difference vanishes, it must be because this part vanishes. This part becomes 0, which means you really find a root of w minus lambda times v. Okay, so far we found 2n roots. Now that's not yet a contradiction. We need to show that if the derivative of f achieves a very large value, then you really find more than 2n roots. And that's what we'll do next. So to think about that, suppose there was a point here where the derivative had a very large magnitude. So let's say there's a point here where at this point the derivative of f has a magnitude that's larger than the degree of p. Then what we'll do actually is we'll consider the graph of cosine n theta plus beta. Okay, that's what's drawn here. This is a graph of cosine n theta plus a shift beta. And I'll pick this shift in such a way that the graph for cosine n theta goes directly through this root. It goes through this point where the derivative of f is unusually large. Okay, so I can always do that. And now something interesting happens, because now when I plot the graph for lambda times f, let's see, it has to go through like this. It has to enter this region. And then it has to come out on this side and then continue on. And you see in this way, lambda times f must actually intersect the graph for cosine n theta plus beta 2n plus 2 times. And that's because there are sort of 2n regions here that cosine n theta plus beta partitions this space of inputs into. And the curve for lambda times f is moving through these regions. So it creates at least 2n intersections. But at this point, because the derivative is larger than the derivative of cosine n theta plus beta, the derivative of cosine n theta plus beta is always bounded by n. The graph for lambda times f has to cross into this region, come back into the region before, and then cross again. And this creates 2 additional intersections between the 2 graphs. Okay, so cosine n theta plus beta minus lambda times f theta has at least 2n plus 2 roots. Okay, so now let's see whether this gives a contradiction. We had to do something a little bit strange. We had to add this shift beta in order to find these 2n plus 2 roots. So, but that's not really a problem, because if you go back here and look at the formula for cosine n theta plus beta, then that's also can be expressed as e to the minus I n theta times a polynomial w in e to the I theta. Okay, because adding a plus beta here just amounts to, actually we can write this formula exactly. This is e to the I n theta plus beta plus e to the minus I n theta plus beta divided by 2. Okay, this is the exact formula for cosine n theta plus beta from this identity. And you see that after you divide out e to the minus n theta, you obtain a polynomial in e to the I theta of degree at most 2n. Okay, so we actually obtain a polynomial of degree at most 2n with 2n plus 2 roots, and that's not possible. That's not possible. So that proves Bernstein's theorem. And this is actually maybe a key place where there's a very, very clever trick used to prove Markov's theorem. All right, now it only remains to prove Markov's theorem. And to prove Markov's theorem, we'll use Bernstein's theorem as a black box. Okay. And there are two cases. Okay, the first case is that we're interested in inputs x. So now we're proving Markov's theorem, so we're in the setting where we have just polynomials that have real valued inputs. And we want to prove that the derivative of the polynomial is bounded, if the polynomial itself is bounded. There are two regions that we'll consider separately. The first region of inputs is when the magnitude of the input x is bounded by cosine pi over 2n. Okay. In this region, what we'll show is that the magnitude of the derivative of a bounded polynomial must be bounded by the derivative of the Chebyshev polynomial at the point cosine pi over 2n. Which we've already established that the Chebyshev polynomial has derivative bounded by n squared everywhere in the interval. Okay, so the only thing we need to prove here is this first inequality. And to see this, we'll just use the chain rule again. So just imagine, let's set f of theta equals to p of cosine theta and apply Bernstein's theorem. When we apply Bernstein's theorem, what we get is that n is an upper bound on the derivative of p at cosine theta times minus sine theta. This is from Bernstein's theorem. Okay. So here, again, I'm using the fact that the degree of p is n. The degree of p is n. Okay. But that's equal to, it's at least, now, notice that this equation here, so this implies that the derivative of p at cosine theta is bounded by n, the magnitude of n divided by sine theta. And this upper bound here becomes worse and worse as sine theta becomes closer and closer to 0. Okay. Eventually this upper bound becomes really bad when sine theta gets very close to 0. That's why we can't use it to reason about all values of cosine theta. Okay, that's why we're only limited to this case. But in this case here, what happens is that the worst bound you get here is when sine theta is as small as possible, and that bound occurs when theta is equal to pi over 2n. Okay. Because sine theta increases as cosine theta decreases. So, and now to bound this expression, I'll use the fact that it's equal to n times sine pi over 2n times sine pi over 2, because sine of pi over 2 is 1. But this ratio is exactly the kind of thing we bounded before. This is sine of n times theta divided by sine theta. And that has magnitude at most n squared, actually. Okay, so, well, actually, first of all, this expression, by what we showed before here, the derivative of t n at cosine theta is n times sine n theta divided by sine theta. And so this thing we've calculated here is equal to the derivative of t sub n at cosine of pi over 2n. So this proves this first inequality. And we've already shown that that has magnitude at most n squared. So this proves that the derivative of p is bounded in this region. Okay. Now finally, the only remaining region is when, oh, this is an error, right? This should say greater than or equal to. The only remaining region is when the magnitude of x exceeds cosine of pi over 2n. And in those regions, for example, when x is larger than cosine pi over 2n, we'll actually prove a really strong bound that the magnitude of the derivative of p is bounded by the derivative of the Chebyshev polynomial. Okay, which we already know is bounded by n squared when x is at most is between -1 and 1, the Chebyshev polynomial. So I just need to prove this part of the claim. So let's prove it. The idea is to consider the polynomial q of x, which is t sub n of x minus lambda times p of x. Lambda is again a number that's very close to 1. Okay. So here's what we already know about q of x. The first thing we've shown already is that we've argued before that in this region here, this region here before this point, cosine pi over 2n, already includes n minus 1 of the n arcs of the Chebyshev polynomial. And that means that in this region before the line where x equals cosine pi over 2n, there have to already be at least n minus 1 roots for the polynomial q of x. And q of x is a polynomial of degree n. So this region already has to have n minus 1 roots. And a consequence of that is that the derivative of q, which is the derivative of the Chebyshev polynomial minus lambda times the derivative of p, has to have at least n minus 2 roots in the same region. And that's because in between every 2 roots of q of x here, has to be a root of the derivative. Right? In between every two roots of q of x has to be a root of the derivative. Every two roots of a polynomial must contribute a root of the derivative. Okay. So q prime of x has at least n minus 2 roots in this region. And now I'll argue, and a q prime is a polynomial of degree n minus 1. I'll argue that if this inequality is violated, then we can find two additional roots for q prime. Now, to see this, the first observation is that right on the boundary here, right on the boundary, we've already established that p prime has derivative less than the Chebyshev polynomial right at the boundary, or bounded by the Chebyshev polynomial. And that means q prime of x has to be positive at this point. It has to be positive. That's the first fact. Now suppose this inequality is violated. Okay, so suppose p prime of x actually exceeds t prime n of x. This means that at some point here, the curve for q prime of x has to dip below 0. Right, it has to become negative. And that generates one additional root right there. Okay. So that's one additional root. And finally, for x it's very large, at some point further down here, q prime of x must have a value that exceeds 0, goes above 0 again, because the leading coefficient of t prime must be larger than the leading coefficient of lambda times p prime. Because of what we argued right at the beginning of this video, the leading coefficient of any bounded polynomial p has to be bounded by the leading coefficient of t. So at some point very far into the future, for large values of x, q prime must become positive again. And that generates another root somewhere here. So we get two additional roots. And overall, we've now found a non-zero polynomial q prime that must have that has n roots. It's a polynomial of degree n minus 1 and it has n roots. This is not possible. Okay. And that means that q prime must be just a constant polynomial, but that's not possible. The q prime could be the zero polynomial. That means that q of x could not have looked like tn of x minus lambda times p of x. Okay. This polynomial has leading coefficient that's non-zero. Its degree n coefficient is non-zero, and there's no way for that to be true if q prime of x is 0. Okay. So this proves that there has to be that this bound holds. The derivative of p is bounded by the derivative of the Chebyshev polynomial. Okay, so that concludes the proof of Markov's theorem. Now, there are a few questions that you can ask yourself to test if you understood all of the ideas I discussed. One is to understand, we talked about the derivative of a bounded polynomial everywhere in this interval, but one thing to ask yourself is, what can you say about the derivative of the polynomial points close to 0, for example. Can you prove a stronger bound when you're interested in bounding not the maximum derivative here, but just the derivative of p at 0, for example? That's one question. Another question is that's a little more tricky that you can ask yourself is, suppose I told you, suppose I don't know that the polynomial is bounded, but for example, maybe there are n points or m points equally spaced between -1 and 1, and the polynomial is bounded on those m points. Its value is bounded on m discrete points that are evenly spaced. Then what kind of bound can you obtain on the derivative of the polynomial on those m points, let's say? That's another interesting question. Okay. So play around with those questions, and I hope you enjoyed the video.